Determining exact distances to bodies in the solar system is based on measuring their horizontal parallaxes. The rapid development of radio engineering allowed astronomers to successfully determine distances to planets using the radar method. The distance to distant stars is reliably determined by their small annual parallactic displacement. 1 parsec is the distance from which the radius of Earth's orbit is seen at 1 second.
Welcome. We're about to conduct a rigorous examination of one of the most fundamental questions in astronomy. How do we measure the universe? We'll be looking at the precise methods astronomers use to chart the heavens, from the planets right next door to the stars light years away. It's a remarkable story of geometry and human intellect.
So, let's begin by framing the fundamental problem. For centuries, this question was a monumental barrier. How do you measure the distance to something you can't touch, something you can't reach? We can't exactly stretch a tape measure across the solar system. The solution, as it turns out, is not physical, but geometric. It relies on observation, trigonometry, and a very clever understanding of perspective.
Here is our agenda. We'll proceed through these 5 sections, building our understanding of cosmic distance from the ground up. We'll start with the problem itself, then move to our own solar system, before tackling the much greater distances to the stars, which will lead us to a whole new unit of measurement.
All right, Section 1. The core challenge here is that the night sky appears to us as a two-dimensional surface. It looks like a great dark dome with points of light stuck to it, but we know it has depth. The challenge then is to perceive and measure that third dimension, the distance, using only observation and geometry from our single vantage point on Earth.
The solution to this problem, the key that unlocks that third dimension, is a principle known as parallax. You've experienced this thousands of times. If you're driving in a car, you'll notice nearby fence posts zip by, while mountains on the horizon seem to barely move at all. That apparent shift in an object's position due to a change in the observer's position, that is parallax, and it is the absolute foundation of cosmic distance measurement.
Now, let's apply this to our own cosmic backyard. The first technique we'll examine is horizontal parallax. This was the first successful method for gauging the distances to bodies within our solar system.
The concept is this. We use the Earth itself as our viewing platform. Imagine 2 observers at 2 different locations on Earth's surface, let's say one in Paris and one in Cape Town. If they both observe the planet Mars at the exact same instant, they will see it projected against a slightly different pattern of background stars. This small apparent shift is the horizontal parallax, and with it, we can triangulate the distance to Mars.
Before we get to the formulas, you can demonstrate this for yourself right now. Just follow the steps on the slide. Extend your arm, hold up your thumb, and look at it first with one eye closed, then the other. That jump you see? That's the parallax shift. The distance between your 2 eyes serves as the baseline for the measurement. To measure the cosmos, we simply need a much larger baseline.
So here is how we formalize this observation with geometry. We construct a right-angled triangle in space. As the diagram shows, the point T represents the center of the Earth, O represents the observer on the surface, say, at the equator, and M is the celestial body, the moon, for instance. The crucial part here is that we already know the length of the line segment from T to O. It's simply the radius of the Earth. This known length becomes our baseline.
And this is where trigonometry becomes our computational tool. The formula itself is straightforward. The distance, which we call delta, is equal to Earth's radius, r0, divided by the sine of the parallax angle p0. For the very small angles we encounter in astronomy, we can use the small angle approximation you see at the bottom. It simplifies the calculation but remains incredibly accurate. It's an elegant application of basic geometry to an enormous problem.
Now, parallax was revolutionary, but in the 20th century, we developed a more direct, physical method for measuring our solar system, radiolocation, or as it's more commonly known, radar ranging. This method doesn't rely on angles, but on the constant speed of light.
The development of powerful radio technology provided this new tool. As you can see, the first success was bouncing a radar signal off the moon in 1946. Just over a decade later, we were accurately ranging Venus, Mars, and even Jupiter, providing an independent and highly precise verification of the distances first calculated using parallax.
The principle here is remarkably simple. We transmit a powerful radio pulse toward a planet and start a very precise timer. We then wait for that pulse to reflect off the planet's surface and return to our detector. We measure the total round-trip time, t. Since we know the speed of radio waves, c, the speed of light, the distance is simply the speed multiplied by the time. We then divide by 2 to get the one-way distance. It's direct, it's precise, and it's brilliant.
All right, horizontal, parallax, and radar work beautifully for our planetary neighbors. But for the stars, they're completely inadequate. The stars are so distant that from 2 different points on Earth, their parallax shift is immeasurably small. To triangulate the stars, we need a baseline that is orders of magnitude larger than the Earth's radius.
So, what is the largest possible baseline available to us? It's the diameter of the Earth's orbit itself. This is the ingenious solution. We take a measurement of a nearby star's position in, for example, January. Then we wait 6 months. In July, the Earth is on the opposite side of the Sun. We then take a second measurement of the same star. Our 2 observation points are now separated by about 300 million kilometers. This is the foundation of the annual parallax method.
This new parallax angle is called the annual parallax, represented by the Greek letter pi. It is defined as the angle that would be subtended by the radius of Earth's orbit, as seen from the star. We are observing the tiny, apparent wobble of a nearby star against the backdrop of much more distant, essentially fixed stars, caused by our own planet's motion through space.
And you'll notice something wonderful here. The formula is structurally identical to the one for horizontal parallax. The distance to the star, d, is our baseline a divided by the sine of the parallax angle, pi. But now our baseline a is 1 astronomical unit, the average radius of Earth's orbit. We've simply scaled up our triangle to interstellar proportions.
This method of annual parallax is so fundamental to measuring stellar distances that it actually gave birth to its own unit of distance. And that brings us to our final section, the parsec.
Unlike meters or miles, which are historically arbitrary, the parsecs definition is derived directly from the geometry of our measurement. Its very name is a portmanteau, a combination of the words parallax and arcsecond, which tells you exactly what it is. Here is the formal definition. A parsec is the distance to a hypothetical star that exhibits an annual parallax of exactly 1 arcsecond. So if we were to look back at our solar system from a star that was exactly 1 parsec away, the radius of Earth's orbit would appear to be 1 arcsecond wide. The unit is intrinsically linked to the method.
1 arcsecond. This is the defining angle. To give you a sense of scale, an arcsecond is 1/3600th of a degree. It's the angular size of a coin, viewed from more than 3 kilometers away. In truth, no star is close enough to have a parallax this large, but it serves as the perfect, geometrically defined standard for our cosmic ruler.
This table provides the essential conversions. A single parsec is equivalent to about 206,000 astronomical units. That's 206,000 times the distance from the Earth to the Sun. Or, in more familiar terms, it's approximately 3.26 light years. This gives us a tangible sense of the immense scale this single unit represents.
So, to summarize our journey, we have constructed what astronomers call the cosmic distance ladder. Each method forms a rung. We used our knowledge of Earth's radius to measure the solar system with horizontal parallax. Then we used our knowledge of the solar system's radius, the AU, to measure the nearby stars with annual parallax. Each rung allows us to see further into the cosmos.
And I think this quote from Carl Sagan captures the essence of this endeavor perfectly. The geometric elegance of these methods, using simple triangles to map the heavens, is a profound testament to the power of the human intellect to comprehend the cosmos in which it finds itself. But this leaves us with a final, tantalizing question. The parallax methods we've discussed are powerful, but they only work for the stars in our local neighborhood. They cannot reach the incomprehensible distances to other galaxies. So to measure the universe on its grandest scale, we need a whole new set of geometric tools, a new rung on the ladder. But that, of course, is a lecture for another day.
Thank you, friends. Strive for understanding and become wiser. See you soon.